that come into play when you transmit digital data. So, for instance, what we have is this I will call the transmitter, and there is some load, and this is the receiver, which could be a simple inverter, which could be something else. Okay, and this load belongs to the line as well as the receiver itself. Now, ideally, this is all that is there to it. The grounds here and here are at exactly the same potential, and the supplies are the same, and so on. Okay. So, whatever data is transmitted at this point will reach this point, and the receiver will detect value, that is the logical value. But what happens in reality? Firstly, you have a supply, and the supply has some impedance. It could be the impedance of the supply or impedance of the line connecting to the supply. It doesn't make any difference. Similarly, on the ground line, there is some impedance. And you don't have just one transmitter connected to it, you can have multiple transmitters or any other unrelated circuit also connected to the same power supply. Okay, so let's just take an example where two inverters are connected to the supply, and the lines connecting the inverters to the supply also have some impedance. Of course, if two inverters are all you have, you can perhaps design it so that this impedance is very small, but you have other circuits as well. I mean, you can have some other logic block sitting here. Okay, so this is what we have. And similarly, on the receiver side, it could be a different supply altogether, right? It could be operating from a different supply, or it could be operating from the same supply. You can't say. So sometimes when you have transmitters and receivers separated by some distance on a PCB, they are operating on different supplies. Of course, when you think of things like Ethernet, you have one computer and another computer, they are obviously on different supplies, which also has its own impedance. So I have used this to denote the impedance common to all the circuits, and each circuit connectivity has its own impedance, like here, here, and so on. And also the two grounds are connected together. But what is a ground? It is some point in the circuit, so we will assume that it's connected like this. So we generally refer to all voltages with respect to some ground, and that ground is supposed to be equipotential and so on. And we assume that the same ground potential holds for all of the circuits. In this case, for instance, what we imagined would happen was something like this, that these two would be connected. But they are not connected by a zero impedance line, they are connected by some non-zero impedance. Okay. So this is how it goes. So what are the problems you see now in this case? Of course, we connect this, the output of this to this one, and whatever data is transmitted at X should be seen at Y, and this the receiver should faithfully reproduce the data. What problems do you see in that direction? Will it always be able to reproduce the data that was transmitted? Or is there no problem at all? I mean, this is fine. So one of the problems is that, let's look at an inverter. Let's say this is the receiver and perhaps also the transmitter. Now we normally say that this is the input and this is the output, but the voltage is measured always between 2 points. So what does the inverter respond to? Which voltage does the inverter respond to? Huh? Between input and ground? That's it? Between input and ground? Ground of? Yeah. So basically between this and this. That's what you're saying. So actually the NMOS part depends on, NMOS part responds to the voltage between the input and ground. The PMOS part responds to the voltage between input and VDD. Okay. That typically by itself is a bad thing to have. At least if you know analog circuits, you know that this is the kind of thing that gives you problems when the power supply fluctuates, right? Because the sum of these two voltages is the power supply. So if the power supply fluctuates, one of these at least will change. So which means that the output will respond to the power supply as well. It is supposed to respond only to the input, but it also responds to the power supply. But if you didn't have the PMOS, you had only the NMOS part, and let's say you had a resistor in place of the PMOS, then it would not respond to I mean, it would respond to the power supply, but differently. Okay. So, looking at this, what happens is, because all these inverters carry current, we saw that when there is a low to high transition at the output, a current flows here, and when there is a high to low transition, the current flows here. Okay. Now, this is again not the only circuit connected, that becomes clear if you look at this. So, this is the inverter of interest. Okay. So, if there is a, let's say, a low to high, high to low transition of this inverter, you see a current through this path, which also goes through this. Okay. So, which raises the potential here and consequently here also. Okay. With respect to this point. So, actually I also, there is one other assumption, I connected this impedance here, it could be connected here as well. Okay. Huh? Oh, I meant it is connected here, but it could be connected here also. That depends on how it is wired. Or there could be some more impedance between this point and where the signal returns. Okay. So, there are two things. One is, when the inverter is charging or discharging a load, the ground potential will change because currents will flow through the VDD and ground. In fact, both the VDD and ground potential will change. If you look at these 2 points, the voltage between these 2 points is the supply to that inverter, and that will change depending on the current through the inverter. Okay, and not only the current through this inverter, it also depends on current through every other circuit that is connected to the same supply. Okay, because they also draw currents from the same VDD and ground. So, there can be a problem when, let's say, this is supposed to give a logic high, but then there happens to be a drop like this, logic low, but there is a drop in this direction. Okay. So, the total applied here could be more than the total that is given out by the inverter. Okay. So, it detects it wrongly. Exactly how much is the problem depends on the situation, how large the circuit is, and so on. The larger the circuit, the more problems you have. Okay. If you think of 2 chips on a PCB, the ground potentials could be different by hundreds of millivolts. And it's not the DC ground potential that is different. DC ground potential could be very close, or even that will be different, but maybe not by as much. But what is more dangerous is the dynamic change, because the inverter draws a lot of current when it is charging a load. Okay, charging or discharging a load. So, during those instants, the drop across these parasitic impedances can be quite large, hundreds of millivolts. Okay. So, that can give you problems. So, you have fluctuation on VDD and ground lines, which basically means that dynamically the characteristics of this inverter are shifting. Okay. The characteristics of the inverter look like this. This is the threshold voltage of the NMOS transistor, and this is one threshold of the PMOS transistor below VDD. Okay, that is this. Now, what is this VDD? The VDD is what appears locally at the VDD of that inverter. Similarly, this is not VTN; it's VTN plus V ground, where V ground is the local ground potential of the inverter. So, depending on, and this is not the same for every inverter. So, the characteristics of several inverters could be shifted. Okay. So, in the worst case, it's possible that the inverter will not detect the logic correctly when it's sent by another inverter. So, for instance, if normally a voltage here should be detected as a high logic and a low output should be given. But if the characteristic of the inverter is shifted so much, you will get a high output if there is a big shift. And a big shift is possible. I mean, big shift meaning it can be hundreds of millivolts, drops across grounds and VDDs and so on. Okay. And again, this is a problem that gets worse at high speeds. At DC, there is no problem. We assume that the parasitic drops, the parasitic resistances are small in these branches, okay, in ground and VDD. But as frequency increases, firstly, inductances start coming into play. So, the impedances themselves increase, these impedances, because they are combinations of R and L. The additional problem is that the currents also increase. right? Because the current depends on the frequency. So you are getting hit from both sides. The current increases and the impedance increases. So the drops keep on increasing. So how would we solve this problem? You've all been in the lab. Yeah, that's one thing, but without redesigning the circuit, if you wanted to make the same circuit better. So that is why you use what are known as supply bypass capacitors. So firstly, let's take these two impedances. Now these two impedances can be large, and if high frequency currents flow through this, you get high frequency drops. But let's say you had a low impedance path between this point and this point for high frequencies. Okay. Then high frequency current would not flow through this, but it would flow through the capacitor. Okay. And for this to happen, obviously the reactance of the capacitor should be much smaller than the supply impedance. So if that's the case, then the drop across this will be small. Okay. So the parasitic drop will be small. So this is why you use supply bypass capacitors. And of course, if you could bypass each inverter, you would also do that. If you can connect a capacitor here, then that also makes sure that the voltage between, let's say, point A and point B is constant. Okay. Constant, that is for some period of time. It cannot be forever constant. Now, how much that time is depends on the value of the capacitor. The larger the value of the capacitor, the more time it holds the charge. So the more time it holds the voltage constant. Okay. But of course, the larger you make the capacitor, the physical size of the capacitor becomes larger, and its own impedance keeps on increasing. Okay. The capacitor also has a series resistance and a series inductance. That itself will get worse if you make the capacitors large. So if you have built discrete circuits on PCBs, you would have seen. So there is VDD line and there is the ground line, and let's say there is some chip here. So you would see not just one bypass capacitor, but several. Do you know why? What are the values of these capacitors that you would see? Do you remember? Have you built circuits? You must have built circuits in the lab, right? Even digital circuits need this. So nanofarads, all of them are the same? Huh? Yeah, why do we do that? Why do we have multiple capacitors in parallel? Why don't we just put one that is equal to the sum of all of these? Yeah. And why won't the larger capacitor cut out at a larger frequency? The reactance of a larger capacitor is always smaller than that of a smaller capacitor, right? It's 1 over omega C. No, I mean, in any case, these three capacitors are equal to the sum of the three values. Huh? Noise. How will that reduce noise? Yeah, why won't I put one capacitor that is equal to the sum? Or let's say for instance that I had 1 microfarad, 100 nanofarad and 10 nanofarad in parallel. In fact, I'll say, okay, I don't want all this. I'll replace all three with a single 2 microfarad capacitor, which is even greater than the sum of all this. This was 1.11 microfarad, right? Would I do this or not? Equally distributed. So what will happen? In a bigger size, it will be more. What is likely? So you think of a large capacitor and you think of a small capacitor. In which is the parasitic resistance likely to be higher? In a large capacitor. Why? Think of just parallel plate capacitors. So it may be the same, it may be less. Actually, it depends on the structure of the capacitor. What else? What other parasitic elements are there? Series inductance, that is the bigger problem. So let's say you have a 1 microfarad capacitor, and it's not just this. You have a series resistance, which is typically called the ESR, and a series inductance. Okay. Now, if you had only the capacitance, the reactance, the impedance of the capacitor would fall down with frequency. At what rate? 20 dB per decade. What happens if you add the series resistance? What will the plot of the magnitude of the impedance look like? Huh? It will flatten out after a while. So it's a series combination, right? So the impedance of the resistor by itself will be something like this. Okay. And the impedance of the combination is sum of the impedance of the capacitor and the impedance of the resistor. And you know how to sum on a Bode plot, you just take the higher value. So it follows this up to here and does this. And what happens if there is an inductance? Huh? Okay, where will it start rising? Let me say that the inductance by itself had this. Okay, what will it do? Or let's say to make things more interesting, let's say the inductive impedance was like this. This is just omega times Ls. So what happens now? So actually what will happen is, it will of course follow the higher one. So at low frequencies it will look like this. And at high frequencies it will look like this. But there is also a resonance, series resonance. So the impedance reaches a minimum and the minimum value equals Rs of course. And then it rises like this. Okay. So this is what you see. So in this region it behaves like a capacitor. In this region it behaves like an inductor. And simply because the inductive reactance dominates over the capacitive reactance. So given this, what is the answer to what we did before? Can we use a single 2 microfarad capacitor? Actually, there are two things. Firstly, even if the series inductance was the same, as you keep reducing the capacitor, it will resonate at higher and higher frequencies. Okay? But the series inductance itself is also not the same, because a smaller capacitance has smaller size and smaller leads. So it has smaller series inductance. So what you will see is, so if this is the curve for a 1 microfarad capacitor, perhaps for a 0.1 microfarad capacitor, the impedance is higher, definitely, because it is a lower capacitance value. But then it will resonate at some other frequency and then it does this. The inductance is lower. So there is a region where the impedance of a 100 nanofarad capacitor is in fact lower than that of the 1 microfarad capacitor. Okay, that is where it is behaving inductively, right? Or even capacitively here. So in this region, a 100 nanofarad capacitor has a smaller impedance than a 1 microfarad capacitor. That's because it's not just a capacitor, it's a combination of R, C and L. Okay. And if you take a 1 nanofarad capacitor, it may do this. So effectively, and if you put all of them in parallel, what will be the impedance? So let me draw a new figure, and let me not show the resonant dip. I'll just show it like this. You have one capacitor like this, another one like this, another one like this. So let's say this is 1 micro, 100 nano and 10 nano. What is the parallel, what is the impedance of the parallel combination? So you can follow the smallest one on the Bode plot, okay? So you get a low impedance over a much wider range. That is the advantage of having, that is the reason for having multiple parallel capacitors. In fact, if you go to very high frequencies, you will see even lower values like 1 nanofarad and 100 picofarad being used for bypassing. Okay. So let's say this is the IC and this is the power supply. Power supply means it will be some voltage regulator, okay, not an ideal voltage source. So you put a large capacitor here, maybe a single large capacitor that serves the entire board. Then you have multiple chips that are connected. And let's say you decide to use 1 nanofarad and 100 nanofarad for every chip, okay. You put the smallest capacitor closest to the IC. Why do you do that? So for instance, I have the chip and I have 3 capacitors. Let's say these 3 values, okay. So which of this is 1 microfarad and which of them is 10 nanofarads? Or does it make any difference at all? Does it make any difference if I make this 1 microfarad and this 100 nanofarad, or maybe this 10 nanofarad and this, the middle one 1 microfarad and so on? Is there something to the ordering of the capacitor? The whole idea of using a smaller capacitor was to provide low impedance at high frequencies, okay. Now if you take a nice capacitor which gives you low impedance at high frequencies and connect it with a long wire to the chip, the point is totally lost, right. The idea of this was to provide low impedance, but now you connect it with a high series impedance to the chip. So the smallest one is connected closest to the IC, right. The next bigger one is connected here. So similarly for each one. So you have made digital circuits, right? Some pretty big digital circuits. You didn't use any bypassing at all. What frequencies were they working at? Or did they work? In the analog circuits lab also you did some bypassing, right? Or you didn't do it? Not so many, but did you do any at all? Yeah. So this is why you use them. And if you look at the schematic of a board, especially at higher and higher frequencies, you will see that every chip will have a bunch of parallel capacitors. In a schematic, it looks kind of senseless because the parallel combination of the capacitors is simply the sum of the capacitance values. But that's not the reason. That is the reason to use it is because each thing there that is denoted by a capacitor symbol is not simply a capacitor. It is this combination. So to get low enough reactance at high enough frequency, you have to do this. And if you have RF chips, the bypass could be as low as 100 picofarads, and there can be bypass on the chip as well. Because when it's 100 picofarads, you can put it on chip also, right? So this is how you can combat that problem, that you have noise on, you have interference on ground and VDD lines because of currents that are flowing, because of transient currents that are flowing, and you can bypass the supply. This is known as a bypass because it gives you a low impedance path between these 2 points, okay, at high frequencies. Yeah, if you, the line that you use to connect also has some impedance, right? So for instance, you connect a capacitor like this. This is the capacitor and this is the chip. And the line between the two also has an impedance. Now, the idea of using the small capacitor was to get low impedance at high frequencies. Now, let's say the impedance of these two inductors taken together is something like this. Then what happens? The impedance that you get because of the capacitor is not this one, but this. Okay. So, the smallest one should have the smallest series inductance. That's why you put it there. Now, if you put it in series with a large inductance simply because you put it far away, then you have totally lost the purpose of the small capacitor. So, the smallest one should always be very close to the package. And it's also, it turns out easier to do because the smaller one comes in the smallest package and you can also connect it closest. Okay, it needs, you can connect it with small leads. A larger one necessarily has a larger package, larger volume and area. So, you have to take a longer lead and connect it. So, effectively the circuit looks like this. You have the chip and perhaps very small impedance here and here, and let's say 1 nanofarad capacitor. And just because of physical constraint, 10 nanofarad capacitor will be farther away, and a 1 microfarad capacitor will be much farther away. Okay. Now, if you connected the 1 nanofarad here, the effect of this inductance would totally kill the effect of the capacitance. No, it is not. The chip is drawing high frequency current. We don't want it to go through the supply lines. Okay. So, let's say I didn't have these capacitors. Is the point of this clear to everyone, or should I go through this again? I have a supply. Let me say even an ideal voltage source. Okay. It's connected to this chip and it could be connected to many other chips. Now, the chip draws high frequency current based on the switching activity inside. Okay. So, every time there is a, let's say it's a CMOS chip, every time there is a 0 to 1 transition anywhere in the chip, current is drawn from this terminal, and every time there is a 1 to 0 transition, a current is pushed into this terminal. What happens when when you have currents here? You will have a drop and you will have a drop here. Okay. So, the voltage between these 2 points, which is really the VDD and ground of the chip. It's not, I mean, what voltage you have here doesn't matter, okay. It's the voltage that is supplied to the chip that matters between this VDD and this ground. And that depends on the currents flowing through the chip and the impedances. So, the voltage here is reduced compared to this one, and also it's reduced in some complicated way with time, because you don't know, you can't really predict exactly when switching occurs and how much current is flowing and so on. So, it will keep on changing. So, it's to avoid that you provide this. So, now the high frequency currents from the chip will flow through this capacitor. They won't flow through the impedances. Is this okay? Yeah. So, each time an inverter switches from, so if it switches from 0 to 1, you will have a current here which rises and then falls down to 0. Let's say there is no leakage and no static power and so on. Okay. And each time there is a 1 to 0 transition, there will be a current here which also has a similar shape. Is that okay? Current through the? No, it is clearly not constant, right? The current flowing here is constant. Okay. So if let's say this is absolutely constant, so it is DC, and DC through an inductor has no effect. All of the high frequencies are pulled through this one. Is this clear or no? So I mean, you can just carry out this exercise. So let's say you have some I chip. Let's say you have some I chip and a supply with some impedance. Okay. So let's say LS by 2 and LS by 2, and you can also consider some series resistances. Okay. So you can figure out what the voltage is here depending on the ideal supply and these impedance values. Okay. It's simply this VDD minus the drop across LS and RS, and the drop across LS and RS can be found out by looking at the frequency components of I chip and multiplying it by the impedance at those frequencies. Okay. Let's say I chip is a sinusoidal current at 1 megahertz, then you look at the impedance of LS and RS at 1 megahertz, and that is the voltage drop. Now you have this capacitor also. What will be the voltage? You can sit and calculate it. It's not difficult. I in fact encourage you to do this. You assume that I chip is some sinusoidal current and find the value of C so that the drop is minimized. Now, of course, the sinusoidal frequency, sinusoid is not typically at one particular frequency. It can have variable frequency. So you may have to try to choose the capacitor so that the drop is small over a wide range of frequency. Yeah. Yeah. The chip needs those currents, right? So if the chip is driving some load, how will it drive this load? So to put charge on this capacitor, there should be some current flowing here. And that current, in case of a CMOS chip, comes through the power supply like this. It will come, yeah, if it goes into the chip, and here it comes through the capacitor. Why? Okay. The average current comes through the inductor and the resistor. Okay, let's say it's like this. And you have a current. And this current has some DC component and some time varying component. Okay. So for instance, let's say this current waveform was looking like this. So these are all the points at which you have 0 to 1 transitions on chip and the current is demanded. Okay. Now this has a certain average value, and so you can represent this as the sum of the average current and another, this is an AC, right, whose average is 0 by definition because you took the average out in this one. So if you put a large enough capacitor here, let's say an ideal capacitor, what happens is the average current will flow through this and the AC part will flow through this. The average current always flows through this one. So this is the voltage source that is still supplying power. But the AC part, if the AC part flows through this, you have a problem because you will have a time varying voltage between the VDD and ground terminals of the chip. So you make the AC part flow through a capacitor. Is this clear? Anyway, you can also simulate a simple inverter or something and then see this effect. Okay. So one technique, if you do have a CMOS chip, is to try and bypass it as much as possible. Okay. And that anyway you have to do in any real situation. So if you design a board and so on, you have to make provision for bypass capacitor. But a better thing to do would be simply not to have these transient currents. Right. We have all these problems because of the transient currents. So if we don't have transient currents, it will be much better. Okay. So we'll see how to do that. So one of the problems with CMOS architecture is that you have transient currents through VDD and ground when you have switching transitions, and that gives you variable drop across the supplies. Now this has many problems. First is, this is called noise. I'll come to this terminology later. So this again, we are always worried about something that varies with time. If it is constant, it's not so worrisome. It's just like having a slightly different power supply voltage. Okay, that is also a problem, but not as big a problem as this one. Now, secondly, it's not only because of the circuit that you are interested in. So you have your circuit here. Now the power supply here depends not only on what signal is passing through, what signal is being driven through this inverter. It also depends on every other circuit that's connected to this. Okay, so you have something else connected here. So depending on the switching activity inside this block, the supply will change. So that is like having crosstalk. Okay, there are different kinds of crosstalk. We'll see those things. So crosstalk is where one signal affects the other signal. Okay, one way for crosstalk to happen is you have signal 1 and signal 2, the two wires cross each other. If that happens because of coupling capacitance between these two, when signal 2 makes a transition, some of the transition appears on signal 1. Is this clear or no? I mean, I see many blank faces. If you don't understand it, let me know now itself. So, let's say you have a wire and you have another wire next to it. And for argument's sake, let's say the second wire is floating. The second wire has some capacitance to ground, and there is a coupling capacitance between the two wires, which I call C12. If I have a pulse of 1 volt here, what do I see on this? So, you will also see a pulse on this, which is of amplitude C12 by C12 plus C2. Okay. Depending on relative values of C12 and C2, this may be high or low. Okay. And typically this is not floating, you will have some impedance to ground, in which case what you see here will not be a pulse. If it was floating, you will see a pulse. If you have an impedance, you will see something that starts out and dies out like that. Okay. But still there will be some signal on line 2 because of the signal on line 1. So that is known as crosstalk. This is also a problem. Why is this a problem? Why? Yeah, so let's say signal 2 is going to some receiver. Now signal 2, the logic level of 2 should be 0, but then this is jumping up. So if there is enough coupling, this will jump up and this will detect a 1. Okay. So if the crosstalk is high enough, you can change the logic state of the other line. So there are two kinds of crosstalk. One is simply because of coupling here, coupling between two signals directly. The other one is because of coupling through the power supply. Because the power supply to every block changes based on the current to every other block, that is also crosstalk. Okay. So you have all these problems, and all these problems chiefly come about because of the power supply current being dependent on the signals that are being driven. Okay. Is that clear? The power supply current is not a constant. It has some average part, which is what we use for calculation of power dissipation, right? The C VDD square F, that corresponds to the average current. Okay. C times VDD is the average current that flows. So the actual current is a spiky current like this, and the average value of this is C times VDD divided by T. But it's not just the average that matters, it's the average matters for power dissipation, but the transient nature of the current gives you other kinds of problems, like the one we have here. Okay. It gives you noise on VDD and ground terminals, and it gives you crosstalk. So it would be much better to have a logic family or some kind of transmission scheme where the current through the power supply is constant. Okay. This is to avoid problems with crosstalk, etc. And for power dissipation reasons, we also saw that CMOS was not the best choice at very high frequencies, because the power dissipation keeps on increasing with frequency. It may be better to have some logic family which doesn't swing all the way from 0 to VDD. So on both counts, CMOS is not the ideal choice. That's what it seems like. So we'll see what a better choice is. Wait a few minutes. You mean the crosstalk because of signals? Okay, that's an interesting question. We can go to that first. So is there some way to avoid this crosstalk? You have signal 1 and signal 2. And on any reasonable circuit, you can expect signal 1 and signal 2 to cross. You have like hundreds of signals probably, and something will cross something else somewhere. Is there some way to avoid this coupling, or maybe if not avoid, reduce the amount of coupling? Concentric. Okay. Yeah. So what you are referring to is each conductor is surrounded by something which is connected to a fixed potential. Okay. That is not dependent on the signal. Now if there is another one next to it which also has a shield, there is no coupling between the wire inside here and the wire inside here. Okay. In other words, actually you can, if you have two wires, you can try and put a shield in between them. Right. So let's say you have signal 1 and signal 2. You don't need a concentric shield, but at least you can put a ground line. I mean, ground itself is not very well defined as we saw, but we'll say that for now ground is defined, and we'll put something that is at a fixed potential between the two. Okay. So now we also have to assume that the coupling between, the significant couplings are between adjacent lines. The ones that are, there is some coupling between this and this directly, but that component is much smaller. So that way you can reduce it. Okay. Someone else said differential. How will that help? So another technique is Let's say one of these two signals was transmitted differentially. That is, both of these wires represent signal 1. And there is some another wire here. Okay. And the way the signal is coded, this has to do with how you code the signal. So before we said the signal is logic 0 if it is at 0 volts with respect to ground, and it's at logic 1, let's say if it's at 1.2 volts with respect to ground. Now we'll do it differently. We'll say that this is, I'll call these conductors A and B. So logic 0 is when VAB is minus half a volt. Logic 1 is when VAB is plus half a volt. You need two voltages to distinguish between the two states. It doesn't matter what they are. Okay, as long as you are able to distinguish between them. So what happens in this case because of crosstalk? So firstly, there are two things. One is the crosstalk from signal 1 to signal 2. So when signal 1 changes, it changes signal 2. By how much does it change? And crosstalk from signal 2 to signal 1. When signal 2 changes, how much does signal 1 change? So the idea here is we assume symmetry, that is physical symmetry between the two conductors and so on. Without that, it won't work. But if that is the case, the coupling between this line and A is the same as the coupling between this line and B. Okay. In signal 1 and this, it will cancel out. You can work it out quite easily. It cancels out. And similarly, between signal 2 and this, what happens is it will raise both of these by the same amount. Okay. Maybe it will increase both of this by 0.1 volt. But you are not looking for that. You are not looking for the voltage of each wire with respect to ground. You are looking for the difference voltage. Since the same voltage couples to both the wires, the difference voltage remains the same. Okay. So if you have signal 2 also as differential, that's even better. Yeah, we are using more wires. That is correct. So the question is the trade-off worth it? And at high frequencies, it turns out that it is indeed worth it. Now the question was, to you transmit one signal, now you are using two wires, which seems like a waste. But we'll discuss exactly, is the number of wires doubled compared to single-ended? It's not. Okay. We'll see how that is. I think we are out of time. We'll look at it. So this again, this also comes into our new logic family. So if we make it differential, we also avoid the effect of crosstalk. So ideally, we would like to have some logic circuit which draws a constant current from the supply, so that we don't have all these parasitic drops through the supply. It should also be differential, so that all these crosstalks will get cancelled out. There is another reason for using differential. I'll quickly outline that. And the last thing is, the swing should be smaller than the entire supply, so that the power dissipation at very high frequencies is small. And you are already familiar with something like that, I think. You know ECL or CML logic? You don't know? Okay, we'll talk about it. So one other reason why you need differential is, so one is crosstalk. The other thing is just the transmission of the signal. Okay. So you are transmitting signal from one inverter to the other. As I said earlier, what you are interested in, what the second inverter sees is the voltage between this point and ground. It's also sensitive to voltage between this point and this VDD. Okay. So let's say the load for this is the input capacitance of this one. And when you drive this from 0 to 1, where does the current flow? Where does the current flow? Okay, I want the complete current path. This is the supply. So where is the current loop? It has to form a loop, right? It can't be that the current starts from somewhere and ends somewhere else. So the way it flows is, and this is the current path for a 0 to 1 transition. What is it for a 1 to 0 transition? So if the capacitor is connected like this, okay, if the capacitor is in fact between this point and ground, it will be like this. Now if the capacitor was between here and VDD, then it would also go through the supply again. Okay. So it depends on exactly how it is connected. It's extremely important to trace these complete current paths when you design PCBs and so on. Otherwise, you will not be able to design something that works. Okay. Why is this important? Firstly, there may be some impedance on this line, the signal line itself. But let's ignore that for now. Let's look at the impedance on the ground line. Now, these two can be very far from each other. Okay. You would make the signal line, and of course, this line is carrying only this signal. But that's not the case for the ground. The ground could be the common ground plane on a PCB or something of that sort. So, this is not the only signal that's flowing through it. So we can get crosstalk, and also even without that we can get some voltage drop across this. Okay, and the voltage drop can reverse the direction also depending on which way the current is flowing. Okay, so in when it is 0 to 1 it is flowing this way, when it's 1 to 0 it's flowing this way. So what's the effect of this? The output of the first inverter is between this point and this point. That is what we define to be the output. Now the input of the second inverter is not looking at the same 2 points. Okay, it's looking at some other points. So although we say that the output of the first inverter is the input of the second inverter, it is not clearly. Okay, because of this common ground. So again, every signal is represented by a voltage between 2 points. So for the receiver to sense the transmitted signal properly, the 2 points that the receiver is looking at should be the same 2 points that the transmitter is transmitting at. That's not the case when you have single-ended transmission, because the ground is common and there is no way that you can ensure that the potential here is exactly the same as here. Now, as frequencies reduce, this becomes less of a problem. As the circuits become less complicated, it's also less of a problem, simply because there is less current flowing through this parasitic ground. But as the frequencies increase and as the circuits become complicated, this becomes more and more of a problem. Now, this is where differential signal comes in, because in differential transmission, you have two wires dedicated to each signal, and you are only looking at the difference between these two. Okay, so both the receiver and the transmitter, whatever the transmitter is transmitting, the receiver is seeing. So another way to think of differential signaling is that the reference for in this case the ground is the reference point for this signal. So in case of differential, you use a separate wire so that the reference is also sent along with the signal. Okay, so there is no other signal flowing through these, right? These two are dedicated for this signal. If something is going this way, some current, the same current should be coming in the opposite direction. So a differential provides the reference automatically, because you have two wires and you are looking at the difference potential between the two wires. So that way also it helps. So there are so many very good reasons to follow differential architectures at high frequencies. The complication is, of course, that you have to use two wires and you may have to use more complicated logic family. That increases the size, that increases the power dissipation at low frequencies. So it's not worth doing this at very low frequencies. But as frequencies increase, this is the only way to do things, because this common ground, it's a very dangerous thing. I mean, you can't, it's hard enough to track the currents in this circuit. If you have much more complicated circuits, it becomes that much harder. Okay? You can't really trace which way the currents are flowing, how the drops will be, and so on. It becomes really complicated. And you have to keep in mind that the ground is not some simple wire as shown here. It can be some big piece of metal and different things are connected at different points. So if you have a plate and you have currents injected at different points, to find the current distribution on the plate is not a simple thing, right? You have to use some more complicated things than hand analysis. So that's the reason also to go to differential transmission. Okay. Any questions on this? So are you all convinced that differential transmission is good for high frequencies? Or no? You are not convinced? Huh? Why not?